What is algebra? What does algebra deal with? And what will we learn in this course? Let's first start with arithmetic. In school, you learned how to add, multiply, subtract, and divide numbers. You may have learned about fractions, radicals, and other operations between numbers. Arithmetic is useful whenever you have a problem where you can get the answer by calculation. For example, suppose you're going to a store. You look up all the products that you're going to buy in a magazine and record their prices. How much money do you need to take with you so that you have enough to purchase all the products? This is a basic arithmetic problem. You add up all the numbers, and the resulting number is the answer to the problem. In algebra, we rather deal with problems where we need to find the answer without being able to directly calculate what the answer is. Algebra is like a number puzzle. We deal with problems where we have to figure out what something is from the condition that it satisfies. Here's an example of an algebra problem. In the ancient world, weight was determined by a balance scale. On one side of the scale, say the left side, we place the object we want to weigh. And on the other side of the scale, we place equal weights so that the scale balances. For illustrative purposes, say that the weights were equal-sized stones. Whenever we weigh something on this balance scale, we get the weight of the object in terms of stones. For instance, if on the left side we have an apple, and on the right side we have one stone with the scale balanced, it will mean that the apple has the same weight as one stone. This would mean that one apple, assuming that all apples are equally sized, would be one stone. Let's say instead that two apples are balanced with one stone equally. This would mean that one apple, assuming all apples are equally sized again, weighs a half a stone. If we have three apples balancing with two stones, this would mean that each apple weighs 2/3 of a stone. An arithmetic problem involving scales can be the following problem. Say an apple weighs half a stone and a pear weighs 1/3 of a stone. If a person bought 10 apples and 15 pears, how much is the total weight? This is not a puzzle. We know exactly what we have to do. We know how to add fractions and how to multiply them. So to get the answer, we get 10 times a half, that's for the apples, and 15 times 1/3, which is for the pears. That gets you 5 plus 5, which is 10 stones altogether. This is not an algebra problem because all we have to do is calculate from the information given to us. Now compare this problem to the following problem. Suppose that 7 apples and 2 pears balance with 3 stones. We also know that 2 apples and 1 pear balance with 1 stone. The problem is to find the weight of 1 apple from this information. This is an algebra problem. It's not immediately clear from the information what the answer is. It's sort of a number puzzle. Find the numbers for the apple and a pear, in terms of their weight, that will make those two conditions true. We can try to guess the numbers and see if they work, but that's not easy. The answer does not need to be an integer, which is a whole number, as the weight can be a fraction too. And there are too many different possibilities to check. Instead of guessing, we want a method of solving this problem. Let's see how we solve this puzzle. Note in the course of the solution that our method of solving the problem will be rather clever. This is because algebra is sort of a puzzle, and puzzles need clever ideas to solve them. We start with the fact that 2 apples and 1 pear balance with 1 stone. On the left side of the scale, we have 2 apples and a pear, and on the right side we have a stone. Now, on the left side, we have 4 apples and 2 pears, and on the right side we have 2 stones. The other fact that we know is that 7 apples and 2 pears balance with 3. Therefore, if we take away 4 apples and 2 pears from the left, then take away 2 stones from the right, the balance will be preserved. Because 4 apples and 2 pears equate with 2 stones, so we're removing the same weight from both sides. But when we remove 4 apples and 2 pears from 7 apples and 2 pears, we are left with 3 apples on the left side of the scale. On the right side, we had 3 stones and are now left with 1 stone after removing 2 stones. Therefore, we are left with 3 apples on the left side of the scale and 1 stone on the right side of the scale. From here, we can conclude that the apple weighs 1/3 of a stone. We solved this puzzle by using a clever idea of adding and subtracting equal weights to isolate the apples by themselves without the pairs. We didn't guess the answer. We were able to deduce it, almost like a detective in a mystery, from the information that we had available. At this stage, we can ask 2 questions. First is, why not guess? Why not try integers, say 1, 2, 3, and 4, and so forth, for the weight of the apple and see if it works? After we see that it doesn't, then we can try using fractions, and guess some of them until we find one. The other question is, how am I supposed to come up with that idea to solve this balanced scale puzzle? There's no way I would have thought of doing that independently. The answer to the first question is that it's usually a bad strategy. Sometimes guessing or playing around with numbers does work, and in that case you found the answer. Other times there are so many different choices to guess at that you'll have a very hard time trying to get the answer by guessing at it. If we have a general method of approaching such questions, then we can get the answer pretty quickly. To answer the second question, that's exactly what this course is about. The course is to teach you algebraic thinking. There are important concepts in algebra that do use very clever tricks that on your own would be very hard to find. Fortunately, algebra is a very old discipline in mathematics, and these tricks and clever solutions have been known for hundreds, if not thousands, of years. In this course, you will learn some of these techniques for solving various kinds of number puzzles. The ideas are very general and can easily be applied to many types of problems. Hopefully, by the end of this course, you'll be able to apply this sort of algebraic thinking to different sorts of problems. This is an introduction to what this course is going to be about. Before you can start to do algebra, we need to know arithmetic. In this course, we're going to assume that at least you're familiar with arithmetic. How to add, multiply, subtract, and divide numbers, including positive numbers, negative numbers, and 0, and how to work with fractions, decimals, and percentages. You can do all this by hand, or you can do it on a calculator. It really doesn't matter, as long as you get the right answers. Here is a bit on the notation that we're going to be using a lot in this course. You might write multiplication as x. In algebra, instead, we write multiplication as a dot, or a period. So instead of writing 3x5 equals 15, we would write 3.5 equals 15. Other times we don't even put a dot, and instead we use parentheses. So we can write parentheses 3 parentheses 5 equals 15. There's a certain psychology to using a dot over x. Recall that in the order of operations, something which hopefully you're familiar with, multiplication precedes addition. So if we write 2 plus 3 x4, the correct way of doing this is first to find 3 times 4 equals 12, and then to find the answer by 2 plus 12 equals 14. It's wrong to add first. If we added first, we would get a different answer. We would get 2 plus 3 equals 5, and then 5 times 4 equals 20. The order in which we do numerical operations is important. If we want to say to do the addition before the multiplication, we would place the addition in parentheses, as in parentheses 2 plus 3 times 5, in which case the order of operations says that we perform the operation inside the parentheses to get a different answer. Even if we use the dot instead of x, we would rather write 2 plus 3 dot 4. Somehow it feels like we should multiply the 3 times 4 equals 12 before adding the 2, as in the order of operations. This is perhaps because the dot puts two numbers right next to each other, and so the psychological effect is that we're tempted to perform multiplication before addition. I'm not sure if this is the actual reason for using the dot or not, but it's a useful way of remembering to multiply before adding. The very fact that the multiplication puts two numbers closer together is suggestive that it should be the operation performed first. In algebra, we use letters, typically x and y. The letter x is what we call a variable. It represents some number. We use x instead of a specific number because we want to be general and to indicate that we don't necessarily know what that number is. In algebra, we deal with math problems to which we need to find the answer from the information given, like in the balance scale puzzle. And so we use x or y or whatever other variable to designate this number. Since we don't know what the answer is beforehand, we use a letter instead of a number to keep track of it. For example, take the equation 2 times x plus 3 times x equals 5 times x. What does this mean? The x is a variable. It represents a number. If we substitute any number for x, we have equality. For example, if we let x equals 1, then the equation reads 2 times 1 plus 3 times 1 equals 5 times 1, which is clearly true. If we let x equals 2, then the equation reads 2 times 2 plus 3 times 2 equals 5 times 2, which is also true. It would be 4 plus 6 equals 10. The equation 2 times x plus 3 times x equals 5 times x is telling us that no matter what x we choose, that is, no matter what the value of x is in this circumstance, the equation is always true. On the other hand, the equation 2 times x plus 2 times x equals 5 times x is not true, because it's not true for every number of x. We can see that for x equals 0, the equation 2 times x plus 2 times x equals 5 times x is true, because it would be 0 plus 0 equals 0, but that's accidental. It's true for that particular value of x, namely 0, but for other values of x, say x equals 1 or 2 or 3 and so forth, we can see that the equation is no longer true. Therefore, it is wrong to write 2 times x plus 2 times x equals 5 times x, but it is correct to write 2 times x plus 3 times x equals 5 times x. Here's a bit more on algebraic notation. It's standard to write 2x instead of 2 times x. Recall that the meaning of 2 times x is the same thing as 2 dot x. When we have a number and a variable multiplied together, it's standard to simply place the number and the variable next to each other. Thus, we simply write 2x instead of 2 times x. Not that there's anything wrong with writing 2 times x. If you feel more comfortable writing that way, you certainly can. We only mention it because it's standard notation in algebra that we'll use. So to avoid any kind of confusion later, we'll explain what this notation means. One more remark about this notation. We don't write the number after the variable. We do not write x2. Whenever we put the number 2 next to the variable x, we put the number before the variable. This is simply aesthetics. Somehow it looks better to see the number before the variable. Using this more compact notation, the equation we had above can be written as 2x plus 3x equals 5x. In the next session, we'll begin working with algebraic expressions. An algebraic expression consists of a variable, or several variables, involving different kinds of operations. For example, 2 plus x is an algebraic expression. X plus y is also. X times parentheses 2 plus x divided by 5 minus x squared is another example. These are algebraic expressions, since they consist of variables and various operations between them. In arithmetic, you learn how to compute various operations between numbers. In algebra, we extend these to algebraic expressions. We learn how to combine algebraic expressions by adding them, multiplying them, and so forth. We already saw one example of this, 2x plus 3x equals 5x. So the algebraic expression 2x plus 3x, we can combine the 2x and the 3x to simply get 5x. These sorts of algebraic expressions are simple, but we're also going to look at much more advanced ones. And in the next session, we're going to see how to deal with them.